Greetings to all. This is Dr. P. Lata, Associate Professor from the Department of ECE, St. Joseph's College of Engineering. So, I welcome you all to watch this video for learning number systems from digital electronics. In this session, I'm going to introduce the number system and how can we perform counting using decimal and binary number system, what is the place value for each and every number system, and the conversion between decimal and binary number systems, and what are hexadecimal number system and octal number system, how can we perform conversion between those number systems, we can discuss in this video. First of all, we have to understand what is number system. Basically, number system is defined as a system of writing to express numbers. It is a mathematical notation for representing numbers of a given set by using digital or other symbols in a consistent manner. Actually, it provides a unique representation of every number and represents the arithmetic and algebraic structure of the figure. So, in our day-to-day life, we are going to use number system for counting purpose, counting the events that can be taken place inside the computer or that can be taken place external to the computer. So, in real world, how the counting is performed and how we can utilize the number system for counting the elements of the system. So, everything we can discuss. So, counting in decimal and binary. So, first of all, the number system is a code using symbols that refers to a number of items. Whenever we have array of elements, how each and every element can be represented, what type of code, by using which symbol we can represent those numbering of each and every item in the array. So, for example, we can understand how this numbering can be done in decimal number system and the binary number system. In decimal number system, we are going to use 10 symbols, right? There are 10 elements are available in the decimal number system. So, that's why this system can be called as a base 10 system. Similarly, in binary system, which is used in computer, we can use two symbols. In binary system, only two symbols are used, or two elements or two symbols we can call it. So, those symbols are 0 and 1. So, that's why the system is called a base 2 system. Okay, so in general, what are the types of number system? Common number systems are 4 types in general, which are decimal number system, binary number system, octal number system, and hexadecimal number system. What is the base for each and every number system? The base of each number system is the total number of symbols used in that particular number system, right? So, what are the total number of symbols used in decimal number system? There are 10 symbols are used, which are vary from 0 to 9, all the decimal digits, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Totally 10 symbols are used in decimal number system. It is the system which is used by the humans in our day-to-day life, right? And when you consider the binary number system, it has a base of 2 because it has two symbols, 0 and 1. So, this system, especially this binary system, is very special, which is used in the computer, right? And octal number system having 8 symbols, right? Having 8 symbols which vary from 0 to 7, and hexadecimal number system are having 16 symbols. So, those symbols are 0 to 9 and the alphabets A to F. So, we can have this number system which is having alphanumeric system because it is having decimal digits as well as the alphabet letter A to F. So, these are the number system, commonly used number system. Now, before discussing the conversion between number system, how can we represent a number in a particular number system, everything, how we are going to represent the information in real world and in the computer. So, that I want to discuss in this slide. So, when you consider the electronic switches, these are the elementary storage units inside the computer, right? Each switch holds either logic 1 or logic 0. So the state of the switch, when you consider, they can have only two state. One is the on state or the off state. Otherwise we can say in this way, whenever the switch is open and there is no current flow in that path, so the switch is in off condition. And whenever the switch is closed between two terminal, right, so that switch is closed means there is a current flowing through the path. So we can say that switch is closed, the switch is in on condition. So the on state of the switch is represented with the logic 0 and off state of the switch is represented with the logic 1. So on state is represented with the logic 1 and off state is represented with the logic 0. So if you use only one single switch, we can represent two binary information, right? So state on state and off state, which is logic 1 and logic 0. But when we want to represent the multi-bit information for encoding the real world information, right, we have to use more than one switches. For example, when we connect two switches in series, right, when we connect two switches in series, right, so those two switches can be represented, each switch will be represented with a single bit binary information. The state of the each switch will be represented with a single bit binary information. So for example, when you consider these two switches connected in series, when both switches are in open condition, right, so the open condition or off state of the switch is represented with the logic 0. We have to use 2-bit binary information, which is 0, 0, 0. This 0, 0 is equivalent to digit 0 in decimal. In the same way, if the first switch is open and the second switch is closed, now that condition will be 0, 1 in binary and the corresponding decimal number is 1. So when the third condition, when we consider, the first switch is in closed condition, the second switch is in open condition. So the binary information will be 1, 0, because the closed condition on state is logic 1, off state is logic 0. So which represent 1, 0, 2-bit binary information, which is equivalent to decimal digit 2. The same way, the fourth condition, which is both switches are in closed condition, right, so short circuited, right, so the closed condition of the switch represent on state, so both switches are in on state, so the bit binary information is 1, 1, right, 1, 1, 2-bit binary information is 1, 1, which is equivalent to 3 in decimal. So in this way, the multi-bit information can be stored in the computer by using multiple number of electronic switches. Okay, now consider the information representation in general, how we can use the number of bits, right? So suppose we are going to use n bits, right, that n bits can represent 2 power n different values, right, 2 power n different values can be used, right. So for example, if I am going to use only one bit of information that represent how many values, 2 power 1, which is 2. So two values can be represented. Those two values are only 0 and 1, single bit binary information, because only one switch can be used for representing that one, right. So if I am using 2 bits, that means to store the 2 bits I have to use 2 switches, okay. How many possible values we can derive, means according to this formula, 2 power n, n values 2 here, so 2 power n is equivalent to 4. So 4 values can be derived, can be represented by using 2-bit format. So the 4 possible values are 0, 0, 0, 1, 1, 0 and 1, 1. Now consider the 3-bit binary information. So if I am going to use a 3-bit binary, three number of bits to represent the values in the digital system, so I have to use how many values can be derived, 2 power 3, 8 values can be derived. Those 8 values starting from all 3 bits are 0 and ending with all 3 bits are 1. So totally 8 number of possible combination I can represent. So similarly 4-bit represent up to 16 values, 2 power 4 is 16. So starting from all 4 bits are 0 terminating with all 4 bits are 1. Totally 16 combinations of values we can derive. Okay, now if the number of values are given, how many possible bits can be used, required, that also we can find out. So for example, if 32 values have to be derived, have to be represented, how many bits required? 5 bits are required. How? Use this formula, right? So 5 bits, 5 is the capital N values 5, so the formula is 2 power n number of values, so 2 power 5 will become 32, right, which is equal to 2 power 5, which will become 32. In the same way, when I am going to derive 64 values, to represent 64 values, how many bits are required? 6 bits are required. How? 2 power 6, which is equal to 64, right? So this is how we have to derive the number of bits for the given number of values. So 1024 values I have to represent. For that, how many bits are required? 2 power 10 is 1024. So 10 bits are required for deriving 1024 possible different values. Okay. This is how I can derive the number of bits for the given number of values. Okay. So suppose 40 values I have to represent. So this 40 values is not in the order of 2 power n. So how many bits I can derive? So the minimum it required how many bits? That means 6 bits. How it is possible? 6 bits represent how many values? 2 power 6, 64, right? And if you reduce 1 bit from 6 bit, you will be getting 5 bits. No, 2 power 5 will become 32 bits. So 40 is present between 32 and 64. So how many possible bits are required to represent 40 values means minimum 6 bits are required. So in this same way, we can find out the number of bits for any given number of values. So when we want to represent the binary information, so in this is the way we have to find out the formula. We have to use n bits are required to represent 2 power n different values. Okay. Now consider the decimal number system, right? So we have understood what are the possible representation using binary bits and how many number of values can be derived. So now we can understand decimal number system. The general format for representing the decimal number system is, this is the one, the coefficient is given here, right? So a number with a decimal point is represented by a series of coefficients. What are the coefficients? This is the integer part. That integer part is having 6 coefficients. So what is this suffix number? So a suffix 0, a suffix 1, a suffix 2, a suffix 3, a suffix 4, a suffix 5. What are these represent? The suffix value represent the place value of that particular digit, right? Place value of the particular digit. Now if you consider the fractional part, these 3 coefficients are the fractional part, right? So this fractional part of the number is represented with the coefficients like a suffix -1, a suffix -2, a suffix -3. These are the coefficients present after this decimal point. Okay, so right side of the decimal point. In the left side of the decimal point, we have the integer part of the number, decimal number. Okay, so here what are the coefficients? These are the coefficients which are represented with the decimal digit. 10 digits we have, no, 0 to 9. So the coefficients a will be having the value of any one of the value of the 10 decimal digit 0 to 9. Now what is that suffix? Suffix value represent the place value, which will give the actual weightage of that particular digit position. Okay, it gives the position value or the place value. Okay, now how we can find out the weightage of that particular digit or digit position? So the coefficient for finding the weightage value of that particular position, we have to multiply, that is the coefficient must be multiplied by the place value with the power of 10 for decimal number system. Okay, so this can be represented with the positional notation. So when we consider this decimal number, this given decimal number with the coefficient a, how it can be expressed in positional notation means the a5, which is the most significant digit in the example, should be multiplied with the 10 power 5. So 5 is the suffix, so this coefficient a must be multiplied with the place value 5 with the power of 5. Okay, so this is the weightage of this particular digit A5, right? The same way for position 4, how can we find the weightage? A4 should be multiplied with 10 power 4. Similarly, A3 should be multiplied by 10 power 3. A2 should be multiplied by 10 power 2. So like that we have to calculate weightage for each and every digit position, and you have to add all those weightage to find the magnitude of that integer part. Similarly, for the fractional part of the value, so that coefficient must be multiplied by the place value with the power of 10. So for example, a minus 1, that is the digit, that is minus 1 is the place value. So in this one, that a minus 1 should be multiplied by 10 power minus 1. Okay, so like that we can calculate the weightage for each and every digit in the fractional part. So finally we have to sum all the weightage and find the total value of the particular decimal number. This is how we can find out the we have to represent the decimal number. Okay, so example we can have here, this is the positional notations. So decimal number is having 10 symbols 0 to 9. So the position is very important for representing the weightage for each digit position. Example 7594, 7594, that is the decimal number here. So that 7, the place value is 3, should be multiplied by 10 power 3. 5, the place value is 2, it should be multiplied by 10 power 2. 9, the place value is 1, so it should be multiplied by 10 power 1. In the same way, 4 place value is 10 power 0. This is the least significant digit. Okay, that place value is 0. It should be multiplied by 10 power 0. So the total magnitude of this can be expressed in this way, which is called the positional notation. Okay, so in general we can represent that positional notation for integer part, which can be a0 to an, right? It's a the base 10 number, right, decimal number. So how it can be represented in positional notation? That an, place value is n, should be multiplied with the 10 power n. an minus 1, next lower significant digit, an minus 1, should be multiplied by 10 power n minus 1. So it will go up to a0, which is a suffix 0, which is the least significant digit, must be multiplied with the 10 power 0, which is the place value is 0. So the overall representation of this an minus 1 up to a0 can be represented as a positional notation like this. So typical example, we can have 2.75 base 10, which can be expressed as 2 into 10 power 0 plus 7 into 10 power minus 1, 5 into 10 power minus 2. Okay, so this is the way we can express the decimal number in positional notation for expressing the weightage for each and every digit by multiplying the digit with its place value with the power of 10. Okay, right. Now the other number systems are binary number system, which is base 2, and the weights in powers of 2. Here the weightage can be calculated. The coefficient must be multiplied with the place value with the power of 2, because the base value is 2 here. The same way for octal number system, the number of digit is 8. Total number of digits are 8, which vary from 0 to 7. So the base 8 system, this is the octal number system. So the weights in powers of 8 we have to calculate, right? Then hexadecimal number system, it's a base 16 system, because it is having total number of symbols 16 symbols, which are vary from 0 to 9, which is the decimal number, and the alphabet A, B, C, D, E and F. Okay, so these are the symbols of hexadecimal number system. Now how to calculate the weightage for each and every digit position in hexadecimal? Each and every digit must be multiplied with the place value with the power of 16, right? With the power of 16, because its base value is what? 16. Okay, now with reference to hexadecimal symbols, we can write the corresponding value for each and every from each and every number system, like corresponding to hexadecimal number systems are octal, binary and decimal. For each and every symbols of the hexadecimal number can be represented in octal, binary as well as in decimal. For example, if you consider 0, 0 can be represented in octal is 0 only, and in binary it is 0 only, in decimal it is 0 only. So why, how many digits we have to use in each and every system, that is based on the largest digit of the hexadecimal. When you consider the largest digit of the hexadecimal symbol, which is f, which is actually 15 in decimal, f is equivalent to 15 in decimal, 2 digit number. So that's why we have to represent octal in 2 digit, all the possible digits should be in 2 digit, and decimal in 2 digit. But when you consider the binary, the f can be represented, minimum number of bits required for representing the alphabet f, which is 15 in decimal, is equivalent to 4 bit, right? We need 4 bit, minimum 4 bit we required for representing hexadecimal f. So all possible binary number corresponding to hexadecimal can be represented in 4 bit format. So this is the thing we can understood in this table. For example, when you consider 9 in hexadecimal, that is equivalent to 9 in decimal also, right? But here we have to represent it as 0, 9 as a 2 digit number, because the largest number is f, which is 2 digit number 15. So all the digits, for normalizing the format, we are representing all the digits in 2 digit format. Okay, so what is the binary equivalent of 9? 1001. Okay, and the hexa octal number is 11. How to find out these numbers, right? For the given value in one particular number system, how to find out the other number system? So that is the process is called conversion between the number system, that we can achieve easily, that we are going to discuss. Okay, conversion among bases. How can we, what are the possible conversion processes are available? Each and every number system can be converted to other corresponding number system. For example, the decimal and the number in decimal system can be converted to octal and hexadecimal as well as binary. In the same way, the hexadecimal number can be represented in octal, it can be represented in binary, as well as it can be represented in decimal. This is how we can perform the conversion among the bases, or conversion among the number system. Now, the entire conversion process can be categorized into two groups. One is decimal to any number system, and then any number system to decimal. That's the way we are going to understand. Okay, first consider any number system to decimal conversion. So what do you mean by R? Base R here, actually R is radix, right? The base, the other name for R is radix, right? The first letter of radix is R. So we can call the base system is the base R system or radix system. If R value is 10, that is called decimal. If R value is 8, that is called oct. If R value is 16, that is called a hexadecimal. So this is how any number system, it can be a base 2 or base 8 or base 16. So those system can be converted to decimal. How it is possible? It can be possible using the positional notation. So for example, here the binary value is given, so which is 1101.101. This is the binary number. How it can be converted to decimal number system? Okay, so we need to find out the positional value for each and every binary digit binary bit. Take the reference point as a binary point. From the right side of the binary point we have the integer part, left side of the binary point we have the integer part, right side of the binary point we have the fractional part. Okay, first take the integer part. So the integer part, the most significant bit is 1, 4 bit only we have, no? So the fourth bit, that place value is 3, positional value is 3. So this 1 must be multiplied with 2 power 3 for finding the individual weightage of that bit position. The next lowest significant bit is 1. That place value is what? 2. So that should be multiplied with the 2 power 2. And 0. So bit number 2 is 0 here. That place value is 1. So 0 must be multiplied with the what? 2 power 1. So if you multiply 0 with anything, that will be 0 only. So that's the thing, that part is removed here. So next lower significant bit is what? 1. So that place value is 0. So 1 should be multiplied with the 2 power 0. So 1 into 2 power 0. So like that we can calculate the weightage for each individual bit in the integer part of this number. Then what is 0.101? This is the fractional part. So where the fractional part, the each place value can be represented in negative. So the first bit is nearby the binary point is what? 1. So that place value is -1. So it should be multiplied with 1 into 2 power -1. Next is 0. That is removed here because that value will become 0. And the next one is what? 1. So that place value is -3. So 1 into 2 power -3 we have to mention. So if you add all this individual weightage for each bit position, we will be having the some value which is 13.625. This is the equivalent decimal number. Similarly, we can convert the given octal number to the corresponding decimal value by multiplying each digit with the place value with the power of 8. The same way, the hexadecimal number can be converted to the decimal by multiplying each digit with the place value with the power of 16. Okay, so this is how we can convert any number system to decimal. One of the example here, base r value is 5 is given here in the last example, right? R value is 5. That means it's a base 5 system. 341.24. So what are the numbers symbols will be available? Only 5 symbol which vary from 0 to 4, right? 0 to 4. So this number can be converted to decimal by multiplying each and every digit with power of 5. With the place value, right? Should be multiplied by the place value with the power of 5, so that the corresponding decimal equivalent will be derived. Okay. Okay, so typical example we can understand here. So here 101.11, this is the in this format also we can perform the conversion. 101.110, this is a base 2, it's a binary number. First you take the integer part 101, which can be taken separately. So that 1 place value is 0, 0 place value is 1, and the MSB bit 1 place value is 2. So that 1 into 2 power 0 will produce 1, 0 into 2 power 1 will produce 0, and 1 into 2 power 2 will produce 4. So if you find the total sum of this individual weightage, 1 plus 0 plus 4, which is 5. So 101 is equivalent to 5 in decimal. The same way, if you consider the fractional part 0.110, that 0.110 will give that is the place value. This 1 will we receive the place value -1. The next lower significant bit 1 will represent -2, and the last bit will receive -3 as the place value. Now perform the multiplication. 0 into 2 power -3, 1 into 2 power -2, 1 into 2 power -1, which will give 0 plus 0.25 plus 0.5, which will give 0.75. 0.75 is equivalent to 0.110. So the total value of this 101.110, which is equal to 5.75 in decimal. Okay, so in the same way we can find out what is the decimal equivalent for the hexadecimal number 3B 0.75, 3b 0.75. So here 3b is the integer part, where b is the least significant digit, 3 is the most significant bit. So least significant digit b will be having the place value 0, 3 will be having place value 1. So we have to perform we have to multiply b with the 16 power 0 and 3 with the 16 power 1. So b, actually what is b in decimal? B value is 11. So we have to perform 11 into 16 power 0. So b should be substituted with the 11. So 11 into 16 power 0, 16 power 0 is 1. So 11 into 1 will be having 11 only. Then 3 into 16 power 1, which is equal to 48. 3 16s are 48. So 11 plus 48 will produce 59 as the decimal equivalent. Now 0.5 in the fractional part, that place value is -1, which can be multiplied with 5 into 16 power -1. So 5 by 16 we can have, that value is 0.3125. So 3b.5 in hexadecimal can be converted to 59.3125 in decimal. Similarly, we can perform the octal to decimal number system. 17.32 is the octal number is given. So you yourself, you can identify, you can work out and you can find the solution, verify the solution. So you should get 15.40625 in decimal. How can we perform this one? Now here in this octal to decimal, each and every digit should be multiplied with the power of 8. Okay, wow. So for example, 7 should be multiplied with the, from the integer part, 7 must be multiplied with the 8 power 0, 1 must be multiplied with the 8 power 1. So 1 into 8 is 1, 8, 7 into 8 power 0, which is 7 into 1 is 7. So 8 plus 7 will be giving 71, sorry 15, will be giving 15. In the same way, the fractional part 0.32 can be converted to 0.40625 in decimal. Okay, now we have understood all possible procedure for converting any base system to decimal number system. That means base or to decimal number system we have understood. Now how to convert decimal to any base? That means decimal to octal, decimal to binary, decimal to hexadecimal. How to perform this conversion process? So two methods are available. One for converting the integer part of the decimal number to any other system, and the another one is converting the fractional part of the decimal system to the another system. Okay, converting the integer part to the another system is called as a successive division method. How can we convert the integer part? Means by using successive division method, or converting the fractional part is achieved by using successive multiplication method. So how to perform this one we can see. Now consider the steps should be followed in successive division method. So what to do, right? First, divide the integer part of the decimal number by desired base number, store, quotient and remainder. So when you consider the desired, for example, we may need to convert the decimal to binary. But desired base number is what? 2. So the given decimal number should be divided by base 2, and we have to find out quotient and remainder. This is the first step. In the second step, we have to consider the quotient as a new decimal number and repeat the first step until we get the quotient value as 0. Then the third step, list the reminders in the reverse order. We have to list the reminders in the reverse order to find the actual value in the system. Okay, in the to which we have to derive the number. Then how to perform the successive multiplication method? This method is used for converting the fractional part of the decimal number to the required or desired number system. So first we have to multiply the fractional part of the decimal number by desired base number. Desired base number, it may be a 2, or it may be for octal system it may be 8, or for hexadecimal system it can be 16. Okay, when we want to convert the decimal number to hexadecimal, the desired base is 16. Okay, when we want to convert the decimal number to octal, the desired base system is what? Base number is 8. So like that we have to identify. So that is the first step. We have to multiply the fractional fractional part with the desired base number. Then the second step, record the integer part. When we multiply, right, we will be having the product, right? In that product we have to record the integer separately as a carry, right, as a carry, and fractional part as a new fractional part. So the fractional part should be considered separately. That fractional part should be multiplied again, and that in that product, new product, we will be having the carry that should be recorded separately. So like that we have to repeat the steps 1 and 2 until the fractional part of the product becomes 0, right? So or until we have many digits as necessary for our application. So in that way we have to proceed the step 3. Then step 4, read carries downwards to get desired base number, right? The very first derived carry can be recorded, and one by one we can record it, and we have to record the last carry, and we have to represent the number in the downwards direction. We will see in the example. Okay, this is the example for performing decimal to binary conversion, right? So this is the repeated division by 2 method or successive division by 2 method, right? So how it is performed? Take the example which is 43 is given here, right? 43 is the given whole number in decimal that should be converted to binary. So what we can do? We can perform the successive division by 2. So divide this number 43, right? How many 2's are available in 43? 21 2's are available. The remainder is 1. That is the first remainder. Now take the 21, which is the quotient, right? That quotient must be divided again by 2. So how many 2's are available? 10 2's are available. So the remainder is 1. Then the same way 2 must be divided by 2. Then 10 must be divided by 2. So the quotient will be 5. The remainder is 0. Then 5 should be divided by 2. So 2 2's are 4. So remainder is 1. Now this 2 can be divided by 1, which is quotient is 1 and remainder is 0. Then if you take the remainder 0, the quotient 1, if you divide this quotient 1 by 2, we cannot divide it, right? So the quotient will be 0 and the remainder will be 1. This is the last remainder. So consider here, these are the result we have got. In this result, we should represent the number in this order. The last remainder should be represented as MSB. The first remainder should be represented as the LSB. The first remainder should be represented as a LSB. So the equivalent binary number for the given decimal number 43 is 101011. It is the binary number. This is how we can achieve the decimal to binary conversion by using successive division by 2 or repeated division by 2. Okay, now how to convert the fractional part of the decimal number to binary, right? So which is can be achieved by a repeated multiplication method. Okay, so the decimal fraction, for example, consider here 0.325, that is the decimal number here. So how it can be converted? It should be multiplied by 2, right? It should be multiplied by 2, which will be having 0.625, right? So the carry is what? 0. The integer part of the product, new product, is 0. That should be recorded separately. And the same way 0.625 which can be multiplied by 2 once again. So the new product will be 1.25. So 1 is the integer part which is recorded as a carry separately. Then 0.25 of this product, which is the fractional part, can be again multiplied by 2. So which will be having 0.50. Again 0 is the carry here. Then the 0.50 can be multiplied by 2 here. So which we are getting 1.00. Now this 1 is the carry. So like that we can repeat this multiplication process, right? We can record the integer part of each and every product separately. Now how to find out the final answer in this one? The first carry derived should be recorded as the MSB. The last carry divided should be recorded as the LSB. We should go in the reverse order. Like this we should go. So first carry must be MSB, last carry must be LSB. In the downward direction we have to record it. So 0.3125 base 10 is equivalent to 0.0102101 in decimal. So this is how we can convert the decimal number to binary for both integer part and the fractional part. Similarly, we can perform the decimal to octal and the decimal to hexadecimal. The same procedure we can follow. Right. Now we can understand octal and hexadecimal number system. The octal and hexadecimal number system. In octal number system, we show the number of symbols is 8. Okay, so 8 symbols are there, and in the hexadecimal number system, the total number of symbols are 16. Okay, now how to convert binary to octal number system? What is the procedure? Right, first of all, we have to understand the given binary number should be divided into groups of 3 bits, right? Groups of 3 bits starting from least significant bit LSB, right? If the number of bits is not exactly equal to 3, then we have to add zeros at the most significant end. Okay, we will see in the example. Then the third step, what we have to do, write one octal digit for each 3 bit group. That means for each 3 bit binary should be replaced with the corresponding octal number. For example, this is my given binary number 1010101. So from the most significant bit, we are having totally how many bits? Only 7 bits are having. How to start the grouping the bits? We have to start from LSB bit position. So in the LSB bit position, so 101, this is the first group, right? This 101 will be having the equivalent octal number is 5. And the next group is what? 010. This 010 will be having the octal equivalent, which is 2. Then finally we have only one bit in binary, which is 1. So minimum 3 bits we have to know. Each and every octal should be replaced with 3 bit. So we have only single bit, which is 1. So in the MSB position of this 3 bit, we have to add 2 more zeros. So we will be having 001, which is equivalent to 1 in octal. So this is how we have to convert binary to octal. So the simple procedure is what? So the given binary number should be divided into group of 3 bits, right? And each 3 bit value should be replaced with the corresponding octal digit, right? So in this example, so the 1010101 will be equivalent to 125 in octal number. The same way, we can convert binary to the reverse order, octal to binary, If the octal number is given, that octal number can be converted to binary. In what way? Each and every octal digit should be replaced with the 3-bit binary code. For example, 7 in octal should be replaced with the 3-bit binary code, corresponding code 111. 5 is equivalent to 101. 2 is equivalent to 010. Now what can be the equivalent binary number of 257, which is 010101111. This is the equivalent binary number. The same procedure we can follow for converting binary to hexadecimal as well as hexadecimal to binary. The only difference is in the hexadecimal, when we want to convert binary number into hexadecimal, the binary number should be divided into group of 4 bits. It should be divided into group of 4 bits, right? And each 4 bits should be replaced with the corresponding hexadecimal number. So this is how we can proceed here. So this is the number. The first 4 bit from the LSB bit position is 1011. The second group is 1011. The third group is only 2 bit number, which is 10. With that you have to add 2 more 0. Okay. So you will be getting 0010. So 1011 is B. 1011 is B, the second group. Then 0010 is 2. So 2BB base 16 is the corresponding equivalent octal number for this given binary number. Okay, now consider the reverse process, hexadecimal to binary. What is the procedure? This is my hexadecimal number. How 4-digit number is given? Each and every digit should be replaced with the corresponding 4-bit binary code. So 0 we have to substitute with the 4 zeros. A, which is equivalent to 10 in decimal, which is the binary equivalent is 1010. 5, which is 0101. 2, which is 0010. By combining all this 4-bit group together, we will be having 16-bit binary code for this given number 25A0. Okay, so this is how we can convert hexadecimal to binary. So almost we have completed all the conversion process except octal to hexadecimal and hexadecimal to octal. So this can be achieved through intermediate code, right? Intermediate number system. So this can be achieved either through decimal number system or via the binary number system. The intermediate system, if the intermediate system is going to be binary between octal and hexadecimal, it's a very easiest method for performing the conversion. Okay, so here one of the example I have given, octal to hexadecimal number system, how it can be converted. So first octal number should be converted to binary equivalent, right? Binary equivalent, and then we can convert that binary number to its hexadecimal equivalent. So here is the one whole number is given 635.27 base 8, which is the octal number. The corresponding hexadecimal number, how it can be converted, the octal number, each and every digit should be replaced with the corresponding 3-bit binary code. So 7 is replaced with the 111 in the fractional part, 2 is replaced with this 010, and 5 is replaced with the 101, 3 is replaced with the 011, 6 is replaced with the 110. So this is my intermediate binary system I have derived. Now how it can be converted to this hexadecimal. Now group it, right? From the binary point, you go in the integer part, go from the LSB bit to the MSB bit direction. So first 4-bit group is 1101. This is the first group in the integer part, and the next one is 1101. Okay, so 1101 is D, and next one is 1001, which is equal to 9, and then 1 is left out here. 3 more zeros we have to add, so 0001, which gives 1 in the integer part. The same way in the fractional part, from the binary point we have to travel towards the right direction. Okay, so 0101, this is the first 4-bit group in the fractional part, which is equivalent to 5, and then 11 is left out, and 2 more 0 we have to add here. So 1100 will give the 4-bit binary code, which is equivalent to C in hexadecimal. Okay, now how to convert hexadecimal to octal, the reverse process. So the hexadecimal number is given, right? So that number can be converted to first to the binary equivalent, then the binary equivalent can be converted to octal number. Consider here A3B.7 is the hexadecimal number. Now this hexadecimal number, digit 7 should be converted to 4-bit binary code. B should be converted to 4-bit binary code, which is 1011. 3 must be converted to 011. A must be converted to 1010. Now all this binary number, now it should be converted to octal just by grouping this binary number into group of 3 bits, right? Starting from the binary point to the integer point, from LSB bit position we have to travel in the left direction. So the very first group is 011, which is equivalent to 3. The second group is 111, which is equal to 7. Then the third group is 000, which is equal to 0. Then the fourth group is 101, which is 5. Okay, now in the fractional part, from the binary point we have to travel towards the right direction. So 011 is the first group, which is 3, and then 1 is left out, so we have to add 2 more 0 here. So 100 will give 4. So now this is how we can convert the binary number to octal. So hexadecimal to octal conversion using binary number system as the intermediate system is completed. Okay, I believe that this lecture will give the very good knowledge about the number system in digital electronics. Make use of this opportunity. Thank you for watching this video. God bless you. Happy learning.